Well, it's a pleasure to introduce Hellen Santana. She is from Universidade Federal de São Carlos, who will talk about relative Bruce-Robert numbers and Chern obstruction. Thank you very much, Hellen, and you can start when you are ready.
Thank you, Georgie. Hi, everyone. I am very happy to present my work here in the Brazilian webinar. And I thank my colleagues for the opportunity. So we organized this together, and I am grateful for the opportunity to talk about my work again in the Brazilian webinar. So yes, I will talk about relative Bruce-Roberts number and Chern obstructions. And I wanted to comment how the lecture is organized. So I will talk about a few words about why are we here, and not just few words about why I am here today. And then after that, I will talk about mathematics itself. So in order to present you some results, I got with Cidinha and Bárbara Lima Pereira. I need to introduce four main tools, which is this four one, local obstruction, the Morse critical points, Chern obstruction, and the relative Bruce-Roberts number. So there's many things we need to discuss before I state my results. But I will start with why are we here? So this is something, to organize this lecture, I had to make a decision, which was, should I be emotional in the beginning and then maybe be not really concentrate to present the talk? Or should I be emotional at the end and then maybe scare people to ask questions? So I chose to be emotional in the beginning. So this is it. I might cry, and many of you know me. I am a bit an emotional person, so I might cry. But I need to say, why are we here? So in this semester, we decided to give lectures, invite lecturers to in honor of Cidinha, who unfortunately is not here with us anymore. And the Brazilian webinar of singularity theory, it was an idea of her. So it started with the seminars in ICMC, in USP, right, in São Carlos. So many of you know that once you are visiting Brazil, São Carlos, you would give a talk there, or you would attend to a lecture in the seminar there. I myself organized like the singular coffees that maybe many of you participate, where some minutes before the talk, we get together and drink a coffee and eat something good. And then we go to the seminar, we watch the seminar together. And that was a very warm and good environment to discuss math and to know people, right? And in here, I need to say something that many of us were students in São Carlos, right? Like for the master or PhD or a postdoc researcher or anything. And Cidinha, when we have a talk, Cidinha was the first in line, right? And paying attention, no matter what the subject of the talk was, she was in the front of the room taking notes in her notebook, right? Everybody remembers that. But between us, the students, we had a little joke that the note was an attendance list. So right before the seminar starts, she will look back to see who was in the room, right? To see, okay, this student of singularity theory was not there. So that is not good. So she was super, that was something that she asked of us, for people to attend to the seminar, right? This is, of course, just a joke between us, but she really wanted us to be there, even if you cannot follow the lecture. She I mean, we know now that we are, time has passed. We know that it's important. Even if you don't understand everything, it's good for you to know people, to see what people is doing, because that might be related to you at some point, right? So that was a very, something that is very, everybody remembers that. That's it. So during the pandemics, she had the idea of continuing the San Carlos seminars, but online. And then this idea got together many other research centers. So now we are many that organize and that take this going on, right? So this semester, these lecturers, of course, that was natural to pay tribute during the Brazilian webinar, Singularity Theory webinar, right? Okay, so thank you very much, Cidinha, for teaching us so much. So now is a point where I'll probably be crying because I need to say why I am here. And Cidinha, there are many people that are much more closer to Cidinha than me. Unfortunately, I was not that close to her. I was her postdoc at some point. I'm getting there, but I was not close. So I don't have, like Davi had a super beautiful picture of his family, and Cidinha and Alexandre told us, Elenice told us many stories that are very warm stories that are long stories, right? And it's super beautiful. So of course, I do not have those types of stories, but I think that if I am here, I need to share with you how she was, even for people that are not that close or that do not have like a very big story with her. So this is what I wanted to tell, why I am here in this sense, okay? So I did my PhD in USP, São Carlos, and I organized this singular coffee in the seminars and everything. It was very, very good for me. And after I defend, I got my PhD. So it was in December 2019. So in 2020, I was a postdoc, a voluntary postdoc. So I didn't have any scholarship. I'd have no funding at all. I was not any type of professor. I mean, I didn't get any money from mathematics. I was a voluntary postdoc. And during this year, I organized like the seminars. Of course, it was online, right? But okay, it was in this period I was working with Nivaldo. I was a postdoc of Nivaldo, and Amanda was a student of his. She was doing her PhD, and then we organized. And this was a message of Cidinha. So I took some prints of emails. Okay, so this was the email of Cidinha, and if you were a student in San Carlos, you know that to get a message of congratulations of Cidinha, I mean, it was something important, right? For me, it was very important. So that pays the work of organizing the seminar. So this was then December 2020. All right. And then 2021, the year of 2021, I got many rejections of applications I've made for permanent temporary positions as a professor and also as postdoc, many. I don't have really the number because anyway, I don't have really the number, but it was at least 5 rejections. This in postdocs, right? A part of positions that I applied like for temporary professions, teaching, right? So I gave a lecture, and I think it was in the Brazilian webinar, and I was not in mathematics anymore. I was working in another place because I was like 18 months without any funding. So I chose to move my career. So I stopped stopped what I was trying to do. I stopped research, and I went to work with software, development of software, and that was what I was doing. But I was invited to give a lecture, and I gave, and I took energy from I don't know where to be enthusiastic, because this is what she's saying, that it was good to see my enthusiasm. But I mean, without I was feeling very feeling, and I had the letters of rejection in the mathematics community. So that was a bit of a difficult period for me as a mathematician, because I was quitting mathematics. And I got this email, and that is something that I cannot return ever, right? And she says here, of course, many of you are Brazilians, but I know there are colleagues that are not. So yeah, she was asking if I was applying for positions, and that she hopes I got something at some point. That was November 2021. And I mean, in that year, I decided, so when we go to 2022, I decided to quit math. So my husband didn't agree with that. So Paulo really believed that I could do, and that I could succeed, that I should keep trying, because it was many years of work. But I was super sad about the rejections and not being able to do what I wanted to do, which was teach and research, of course. And then I was like super into this another job that I got. So, okay, I am not welcome at this moment, so I'm going to do another thing, right? And then in April, I think it was April 2022, I got this email of Cidinha telling me and a friend, Rafaela is a dear friend of mine that did her PhD in UFSCar, actually. She was telling us to apply for a postdoc position with her. And I mean, okay, I was feeling super rejected. I was not going to get a postdoc FAPESP with Cidinha, okay? So that was out of possibilities. That was a goal, an objective that I didn't ask God about it, because it was not possible. I mean, it was Cidinha, you know. I'm sure you can understand what I am saying. And then because I applied with others, and you understand what I'm saying, right? And then I only applied for this after these many rejections. I only applied because I didn't want to say no to her. And I am sure you know the feeling. Once she asked something of us, we didn't want to say no, because we knew if that once she was asking something, she was also giving us a direction. You know, it was like, this is a direction I believe you should go. And she could see far ahead, right? So we trust that asking, we trust. Of course, the asking was many times, it was like, okay, I should work on that. I need to work. If I say yes, I need to work. But that was a good direction, because we trusted her. We trusted her gut. Okay, that's it. And then I got the scholarship. I got the funding. So I had quit math already, and I am here now. Nowadays, I'm doing a postdoc in Germany. And I mean, I came back to do this postdoc with her, FAPESP postdoc with her. And then I got a position in a university in Minas Gerais. And after that, I got my position in UFSCar, which is where I work now. And now I am doing a postdoc in Germany. And all these dreams that I got, now that was a dream that was like old dreams, I just got because I get this message of her. So if I am here now, I mean, in Germany, or if I have a position now, it's all because of her, because she chose to to believe or to write an email, because an email of her had power, to make us do things that was good for us, that was a direction and a good direction for us. All right. So this is something I wanted to share with you, my friends and colleagues, because I owe my career, maybe I owe my career to her. So that's it. That was the emotional part of my talk. And now I will go to mathematics, because not only I had the opportunity and the gift of coming back to mathematics, which was my dream, to keep on doing mathematics, but also I got to published a paper with Cidinha. And that also, of course, I didn't ask the postdoc with Cidinha, and no, I didn't ask, for life and universe and God, I didn't ask also a publication with her. So this is really a gift, and something that I am very happy about. Okay, so, and also to work, it was a very good period, because at the same time, Barbara was doing her postdoc with Cidinha, and we could see study singularities of 2 points of view that I'm going to show you, and we got information from that union, right? So that was a very special moment for me. So let me say to you the description. So maybe I am already very messy, but it's fine. On YouTube, I will see after, okay, how is the situation. But so let's see the description of the setting. So I will start with a reduced complex analytic germ, X, in Cn. And I'm going to use a Whitney, for the moment, a Whitney stratification of that variety, right? I will start describing to you, just showing you the definition of an invariant, of a number that have information, gives information about the singularities of a variety. All right. For that, let's see. We have here X, our variety, in an ambient space U, so an open neighborhood of the origin here in Cn. All right. And over U, we will consider this Cartesian product. With U, we are going to consider this Cartesian product. So here we have U and the space of D planes, so a subspace of dimension D planes in Cn, okay? And then what we consider in this Cartesian product is the ambient space of the Nash modification. So here in the Nash modification, I don't think I have any wrote in here, but here in the Nash modification, what we have is elements are points in the following pairs. In the first entry, we have a point in X. And in the second entry, we have a D-plane. If the point is a regular point, we put in the second entry the tangent space to the regular part at that point. And if the point is a singular point, we consider a sequence of regular points converging to that point. The sequence of regular points defines a sequence of tangent spaces, right? Because to each regular point, to each element of the sequence, we can compute the tangent space. So this gives us a sequence of tangent spaces that converges to an element in this Grassmannian. So we put the singular point and the limits of tangent spaces. So here in the Nash modification, what we have is pairs like this, all right? Okay. Then over the Grassmannian, we can consider the tautological bundle. That bundle where we take a D-plane, so an element in the Grassmannian, and a vector in that space, all right? So we can extend the tautological bundle to this Cartesian product, all right? And this extension is what I am denoting by T over here, right? Since the Nash modification has as ambient space these Cartesian products, we can restrict this extension of the tautological bundle to the Nash modification. And this is still a bundle, all right? So what we are going to do is the following. We consider a one differential form. Here I'm taking the distance function, all right? See that we are doing Z1 bar, the conjugates, right? So if you put to it, for example, for Z1, you write like X1 plus I, YI, you know, the complex number. When we make this product, we get X1 square plus Y1 square, right? And this we can do to each element, each entry, because we are in CN, okay? And we are considering the distance function to the square. So we remove the square root, all right? But the thing is that we have this one differential form in Cn over here. This phi that I put here is the projection to the first coordinate, all right? It's only p. It's just that I use p here. So, but this is the projection to the first coordinate. So through this projection, we can consider the pullback of this one differential form over here. And then we restrict this one differential form to the Nash modification, because this is where it is included, right? As sets, at least. All right? So the thing is that this one differential form can be, there are a small epsilon in which you can consider this one differential form to be non-zero. There exists this epsilon. And okay, in this slide, what is happening is the following. So there is this small epsilon in which the one differential form that I called omega tilde. Omega tilde is the restriction of that pullback to the Nash modification. So there is this small epsilon where this omega tilde is non-zero, right? And then the question is, it is possible to extend this one differential form from the inverse image of the sphere into the inverse image of the ball. When I see inverse image, is the inverse image through this map. So maybe here I was not very clear, but this phi here is the projection to the first coordinate, and I am restricting this projection to the Nash modification. This is included in here, right? We are just restricting to the Nash modification. This is this map that I'm putting here, right? So instead of looking at the sphere over here in the bottom, I'm looking at the inverse image of the sphere over here in the top. This is what I am meaning, okay? This is why we are taking the inverse image and not the ball itself. That's all. But you can think, at least to follow, if this is not something that's comfortable for you, you can think about the sphere and the ball. So can we extend then omega tilde from the sphere into the ball without singularities? That is the question, because if you do have omega tilde to be non-zero on the sphere, you can extend it to the interior of the ball by putting zeros. Say that all the points in the interior is zero, but what we want is doing that without the zeros, all right? So this is the question. This type of questions of extensions of sessions, differential forms, functions, this is what the obstruction theory does, right? So we can associate to this situation, we associate a cocycle. It's a cochain. At the beginning, we begin with a cochain, but after the obstruction theory shows that this is actually a cocycle. So this is a cocycle, so an element, a class in this cohomological group, right? So associated to this element, we have the fundamental class, so the correspondent class in the homological group, and we can evaluate one class to the other, right? The cohomological class to the homological class to obtain an integer. We are working over integers here, all right? So once we make this evaluation, we obtain an integer, which is called the local Euler obstruction of the variety at the origin. All right, so this notation here is the notation of, you can think of the cap product or the evaluation itself. Maybe the evaluation is the best one to mention here. All right. So this was a work of Macpherson. There's also independent work of Maria Hellen Schwarz, where she works, instead of working with differential forms, she works with vector fields, and it is it's like the dual construction, but they have done this. Macpherson and Maria Hellen Schwarz have done this independently. And this type of construction can be done also, this is what I'm going to show you now, using a function. When a function defined on the variety has appeared, all right? So I will consider a function Chern with isolated singularity at the origin, all right, defined on the variety X. So the diagram, so the setting is the same, okay? We are in this the same setting. What we are going to change is the differential form we are going to use. This is the difference, okay? So what Brasile Massi, Parmesanense, so this is the work I am following. What they did here was to use the gradient of the function f. So given the function f, we have the gradient, right, which is a vector field. So they construct a vector field that is a stratified vector field. What is the meaning of that? So to each point of our variety, this point, if you have a stratification, this point is in some stratum, right? And then in the strata where we have smoothness, we can compute the tangent space, right? So the vector field we take to, what the vector field does is the following. They take each point of the variety and gives us a vector in the tangent space of the strata where that point is. All right? Very good. So this is what they have done. So this can be constructed actually this is constructed actually in the ambient space, in the ambient space, all right? And again, we can make the pullback to the Cartesian product and restrict to the Nash modification, all right? So let's just understand the following. What would be an element? What would be an element here in this extension of the tautological bundle? As I told you, we need to have it. The tautological bundle at the beginning is just like we take a vector, a D plane, right? An element in the Grassmannian and a vector in that D plane. But we extended the tautological bundle to the Cartesian product. So we have actually triples. In the first coordinate, we have a point of U. In the second, the Grassmannian, the D plane, you put there, and a vector in that D plane, all right? So the thing is that I told you that since the Nash modification is included in here, we could restrict this bundle to the Nash modification and still have a bundle, right? Okay. And what is happening is the following. We take the vector, we have a vector field over here, we look at its pullback, and we restrict to the Nash. So to each point of the Nash modification, think the U tilde here is a vector space, a stratified vector space. So vector field, sorry, vector field. I said vector space, but it's vector field. So to each point of the Nash modification, we get a vector, right? And what do we need here in the fiber? We need the point, a D plane, and a vector. So when we say that U tilde, this construction that we made here, defines a session in the Nash bundle, in this bundle that we restricted here. Maybe I didn't say the name, but the name of the restriction is Nash bundle. So when we say that U tilde gives us a session in the Nash bundle, we mean that we are not taking any vector here. We are taking the vector coming from the vector field. All right? I hope I was clear. If not, you can ask questions. Please feel free to ask questions, okay? So this is what we are doing. Maybe it's clear for everybody, but I wanted to mention this today, all right? I have never said this in other lectures. This is something I wanted to share today. Okay, so this is it. So when we do this, when this U that I put here is not any U, is a U that these authors construct using the gradient, is the conjugate of the gradient, but still using the gradient of a function, right? So when we do this, another number appears, and this number is called the Euler obstruction of the function. So they could produce then this U tilde, which is non-zero over the inverse image of the sphere. The obstruction theory would say what is the obstruction to construct, to extend this U tilde to the interior of the ball. This gives us a cocycle. This produces a cocycle that we can evaluate to the fundamental class, its corresponding fundamental class. We make this evaluation and get an integer. This integer is the Euler obstruction now of the function, because the session we are extending was constructed, was given by the function. All right? It's very beautiful paper, this one of Bracele Massa e Parmesan and Saadi. And the thing is that I didn't put the definition as the evaluation, right? But just to keep going on, this Euler obstruction of a function is also related to a number of non-degenerated critical points. So Saadi, Tibar, and Verzovsk, and I need to say now, right at this point, that it's unfortunate that Tibar also has left us, right? And I pay my tribute to his difficult and beautiful work and contribution to the singularity theory, of course. And in this very interesting and beautiful paper of them, if they prove that if f has isolated singularity, so this Euler obstruction of a function that we saw all this topological construction just now is actually the number of Morse critical points of a deformation, of a Morsification of f in the regular part of the variety. So you see that all that difficulty that we saw, I mean, at least from my point of view, it's not easy. There is a geometric or more a geometric approach to explain to us what the Euler obstruction of a function is doing, right? So if we deform the function f in order to, in the following way, you want to explode your singularity, your isolated singularity, into finitely many singularities that are more simpler, I'm not sure. So they're more simple, that's the first one. In the sense that these singularities would be non-degenerated. How so? The ACN matrix associated to that singularities are non-singular, right? Are non-degenerated, has maximal rank. Okay? So it is possible to do that. And a way to do this is like this. So you sum your initial f with the genetic linear form. So you produce only this finitely many singularities that can appear in all x, so in many strata. But the thing is that the Euler obstruction of a function counts only the ones that appears in the regular part. So the other strata might have this singularity, this singularities also, but the Euler obstruction of a function counts what happens in the regular part. And that is because when this obstruction, here is the setting of the local Euler obstruction, but believe me that once we have the function, the obstruction cocycle associated to the function f, we are also here in this cohomological group. So we are in the top one, okay? So what the Euler obstruction computes, gets, is what is happening in the top stratum. All right? So this is what is happening. So this is what I wanted to say about Morse critical points. Yes. Okay, no. Yeah, this is what I wanted to say about Morse critical points. This is going to come back in the end, all right? This construction that I showed you for the local obstruction and for the all obstruction of a function, these things here, this can be done for any one differential form. I did it, I showed you, okay, I should have removing this, but I showed you with the distance function, this one, the norm of z to the square, and to the differential of a function, the gradient, using the gradient, right? That was for the all obstruction of a function. But that can be done with any one differential form. And using the same approach. So you have now this some general one differential form. So you can also define the all obstruction of the differential form using the same approach, the same tools, okay? This was done by Ebel and Guzenzade. And I am not going into that because it's the same construction I showed you. But they also define an obstruction approach. They study this obstruction approach once you have a collection of differential forms, not only one. The one case we just saw, right? And to study these collections of differential forms, they define the Chern obstruction. So the Chern obstruction, it is what I'm going to tell you now. Okay, I talked too much, but that is what I'm going to tell you now. This Chern obstruction is for collections of one differential forms, all right? And in this sense, since we are not with only one differential form, what is a singularity of our differential form? Are the points where that differential form vanishes. But since we have now a collection of differential forms, we also need to understand what is a singularity in this sense, right? And when we have a collection of differential forms, the singularities appear when we have linearly dependence. So giving a collection of differential forms, a singularities will be when we have a linearly dependence. This is it. But no, this would be a singularity. But this is not only what Ebelin and Guzenzade wants. They also want the following. Not only when we can, for example, restrict our differential forms to the tangent space of the strata where our point is, so we can find the singularity. They also want a condition on the limit of tangent spaces. So remember, if you have a singular point, you can have a sequence of regular points converging to that point. Remember, I told you that already. You see on YouTube after. That gives us a sequence of tangent spaces, and that sequence of tangent spaces converges to an element in the Grassmannian. Let's say L is here, right? Yes, L. So you're not only restricting these one differential forms to the tangent spaces, but also to the limit of tangent spaces, right? And then on these limits, also, we may have linearly dependence. And when this situation happens, we say that our point, the singular point, limit of a sequence of regular points, that point would be in the locus of a collection. And it would be a point in X would be a special point if it is in the locus, so in the loci, in the loci of every collection that we have. This notation over here is not one set of differential forms. It's several sets of differential forms. So to each sub-collection, you see if it is linearly dependent or not. And if it is linearly dependent to each one of those sub-collections, then we have a special point. Okay? So let me see. I don't have the diagram here. I will go back there. Okay? So if we have one differential form, we can produce a section of the dual Nash bundle. Right? Now we have several differential forms in sub-collections, but we have several differential forms. So each one of those those differential forms gives us a session in the dual Nash bundle. So now what we have is not only one of the Nash bundle. We have as many copies of Nash bundles that you need, as many forms you have in your collection. So this is what this very big and scary summatory is saying. Each one of these are copies of the Nash bundle, and we have as many as you need in order to once you have this big collection of differential forms, you have a session in the right bundle. Okay? All right. And then giving this special point, the Chern obstruction of a collection of one differential forms will be the obstruction, because what I mean is the following. So we do have the same construction as you had before. So we had this big, this collection. Over here we would have a collection of differential forms, which is a session of the dual Nash bundle that summatory of Nash bundles. And then you may have an epsilon small enough in which that session, that collection, will be non-zero over the inverse major of the sphere. And then you want to extend into the interior of the sphere, into the interior of the ball, right? So this gives us also a cocycle, an obstruction cocycle that can be evaluated in the corresponding fundamental class, and that gives us an integer, which Hellen and Guzenzade called the Chern obstruction of these big collections of differential forms. All right. So the notion of special point, as we saw, which is in this context, the definition of singularity, right? That special point can also be degenerated or non-degenerated. So you may be able to produce, once you deform your collection of differential forms, you may be able to produce finitely many singular special points, all right, that are all non-degenerated. And the thing is that Hellen and Guzenzade showed that a suitable deformation is like this. So you sum your form with genetic linear function, all right, or form, which coincides, right? And they proved that the Chern obstruction counts the number of non-degenerated special points in the regular part of the variety. Since this is a tribute to Cidinha, I need to say that that construction that was made for one function, for the Euler obstruction of a function, can be done with finitely many functions, all right? And this is the very nice work of Her, Bracelet, and Nivaldo Grulha, where they define the Euler obstruction of a map. And they proved also that the Euler obstruction of a map, when you take this collection to be this one, so here we have a map from X to CP, so we have F1, FP, right? So in the first collection, they put the differential forms of that each component, and they complete with the correct number of genetic linear forms. This correct number here is in order, you need to be able, we need to cut our space in order to be counting singularities, all right? So we may have a very big, difficult singular set, but you cut with the right number of genetic linear forms in order to count the points that appears there, the singular points that appears, all right? In gross modo, it would be this, okay? So they proved that this, looking at this type of collection, this construction depends on the genetic linear form. If they are generic enough, it's not depending on them, on the choice of them. And then they proved that the Euler obstruction of a map is related to the Chern obstruction of this collection of differential forms. All right, it's just a comment because I'm not really defining the Euler obstruction of a map. So since the deformation that we do to produce non-degenerated special points is similar to the deformation we do to produce non-degenerated critical points, in 2022, Grulia, Camila Ruiz, and myself, we proved that the Chern obstruction of DF1, so of this differential form in this space, is the number of Morse critical points of emulsification of the function F1 in the regular part in this space, so in the top stratum of the fiber. All right, so this is merely to understand that once you have Morse critical points, when you're looking at non-degenerated critical points, you are looking also on non-degenerated special points. It is convincible, I know, but this is done in details, okay? So actually our first idea here was to do it in the central fiber, and we could have, we wrote like this, but it was not correct. There was some details to fix. And after doing the postdoc that I told you that I was doing with Cidinha, and I had the opportunity to study it with Barbara also, we could manage to prove in the central fiber also. So this difference, this coincidence happens. This equality is not a coincidence, but this equality happens here too in the central fiber, all right? And actually we could, after we worked on this matter, we saw that we don't have to be only with F1, F2, working only with two functions. We can actually do it with finitely many functions. The argument is the same. Everything fits together, fits very, very well. So it is possible to show then the Chern obstruction of a function form DF on this space. And here what we have, this big capital G here, is a finitely many number of functions, right? Complex functions. And this is the number of non-degenerated critical points of the function f in the space you are looking at, on the regular part of the space you are looking at. Of course, here, just to mention, because, okay, it seems like, okay, so you change from 1 to p functions, but it's not that, right? There are once you have two functions, you wanted to do such things, these types of slices and counting numbers there, critical numbers, singularities there, you need to control somehow the way these singularities behave with respect to each other, the singularities of one function to the other and things like that. All right, so here we are asking f to have a stratified isolated singularity, but we are not asking this for f1 to g1 gp, right? So there are some technical conditions that I'm not telling, that we need to check in order to make these computations, these comparisons. And this is since, as I told you, the Euler obstruction of a function is a number of non-degenerated critical points. We just saw that the Chern obstruction is also a number of non-degenerated critical points. So this is only a clean way to say that this is the equality we have, all right? Now, in the final minutes that I have, I will try to be quick. I am finishing. I told you that the very nice thing that happens, that was the planets aligning, was having Barbara at the same time having a postdoc with Cidinha. So we looked at this setting that we had through the optics with the perspective of the relative Bruce-Roberts number. I think I would be a bit, I would be quick here, not to make you, to introduce more things, because I took a long time in my two first sessions. But the thing is that the relative Bruce-Roberts number is an object, an invariant associated to functions, possibly with non-isolated singularities defined on a variety, which is what we are doing, looking at the Chern obstruction of one differential form and looking at the Euler obstruction of a function. The thing is that the relative Bruce-Roberts number has an algebraic approach, an algebraic definition. And this is very good in order to find examples and give this algebraic approach to these topological things that are not easy at all to compute. So this was very nice. This was a way to give a algebraic approach to this invariant, right? So what we prove, I will be quick here. So what we prove is that we can see the compute the Chern obstruction. That was super topological approach. We can compute using the relative Bruce-Roberts number, which is a dimension of a quotient of modules, as you saw, the complex dimension, right? Minus this summatory. So what happens here, this is very a bit technical, but what we have here is a geometric multiplicity associated to the logarithmic stratification of the variety x, and n alpha here are the number of Morse critical points. So remember, I told you, when we make a deformation of the function, singularities, non-degenerated singularities will appear in other stratum. So the relative Bruce-Roberts number captures that information. The Chern obstruction, no, does not capture that information. It takes only what happens in the regular part, which was here in this slide. We divide, so the part of the relative Bruce-Roberts number that was computed over the regular part of the variety, which is this one. In here, the multiplicity, the geometric multiplicity are 1, all of them, because we are looking at oh my gosh, the word irreducible components. Sorry, we are looking at the reducible components. But I don't want to take too much time in here. But the thing is, this is what we did, right? So we have this number computing more information here, and we got this. Sorry. What have I done? Okay, you have this information. So a relation between the Chern obstruction and the relative Bruce-Roberts number. Just to show you a nice parallel in here, in the same paper where Evelyn and Guzenzade studied the Chern obstruction, they look at the ICES case, the isolated complete intersection singularity, and they prove that the Chern obstruction is this difference of indices. Because in the context of differential forms, there are all other indices that are defined, right? The radial index, Evelyn Guzenzade gave 3 definitions for the Poincaré-Hopf index, right? So in here, we are looking at the radial indices. So they prove that this Chern obstruction, I will... okay, so this is the difference. They prove that this difference of radial indices, and these radial indices are also have this algebraic description. So and in the work they did, it was for any differential form. Okay, it's important, any collection of differential forms actually. Okay, so we did extend a bit what I'm showing to you. We did make a small extension, but we lost a bit because instead of a collection of differential forms, we prove it to a one differential form and the differential form of a function. Okay, so we gain something and lose something, but it's nice to see that this was an equality we had do Evelyn and Guzenzade, and we proved a similar one with the difference of relative Bruce-Roberts number. And this is very nice. For the ICES case, at least, it's something very nice to have this algebraic approach. All right? So this is it. This is a picture of me, Barbara, me with very different hair, but and many years ago with Barbara Lima Pereira and Cidinha. We were in João Pessoa. And Cidinha, we will keep honor you. That's it. Thank you very much.
Okay, Hellen,